All right, welcome to The Explainer. Today we're diving into a really wild puzzle about kinematics, moving through space-time, and honestly the absolute boundaries of physics itself. And we're going to be looking at all of this through the lens of the Immusora scale. We'll explore how we move, how we can actually calculate these massive cosmic journeys using logarithmic magnitudes, and finally, why the universe might literally pull us over for speeding if we aren't careful.
So let me just throw this ultimate travel question out to you. What is the absolute fastest way to get from point A to point B? I know. It sounds like a super basic riddle, something you'd probably ask to pass the time on a road trip. But when we actually apply this question to the fabric of space-time, the answer gets incredibly deep. We're trying to figure out the literal perfect strategy for cosmic travel here. And to do that, we need a good old-fashioned thought experiment. Okay, so imagine this. You're standing completely still. You're right at point O, that's your origin. Your speed is exactly 0 meters per second. Now, way out in the distance is point P, your destination. You're facing it, you're totally ready to go. But there's a catch. You obviously can't just instantly teleport to point P, and you also can't just instantly jump right up to your maximum cruising speed.
And here's the kind of sobering realization that brings us right back down to reality. Changing velocity takes time. Why? Well, because we have mass. Mass is a fundamental physical quantity, and you can think of it almost like the universe's natural resistance to change. If you want to go from standing dead still to moving super fast, your mass basically dictates that you have to pay a toll, and that toll? It's time. You got to speed up gradually.
Which brings us right to our next key concept, acceleration. It's simply the rate at which we change our velocity. Now, what's really cool is how we can calculate this using the Immusora scale. You remember our rule for logarithmic magnitudes, right? It's this incredibly effective shortcut. Instead of dealing with messy division, we just subtract. It's that easy. We just take the magnitude of the change in speed and subtract the magnitude of the time it took.
Let's make this crystal clear with some numbers. Say we increase our speed by a magnitude of 1.0 meters per second, and let's say it takes us a magnitude of 0.3 seconds to pull that off. Using our little magnitude trick, we just do the subtraction. 1.0 minus 0.3 gives us an acceleration magnitude of 0.7 meters per second squared. It's so elegant, isn't it? Just straightforward basic subtraction to figure out exactly how quickly we're speeding up.
But, what goes up must come down. Or, I guess in this case, what speeds up must eventually slow down. Especially if we actually want to stop at our destination instead of just blasting right past it. That's deceleration. Now, fun fact, physics actually uses the word acceleration for both speeding up and slowing down. It's a bit of a quirky terminology thing. Because acceleration is a vector, when you're slowing down, it just means your acceleration is pointing backwards, directly opposite to your velocity. So your speed decreases over time.
Okay, so the crucial part here is figuring out the absolute best travel strategy using these two concepts. Remember, we're at point O and we're trying to stop dead exactly at point P. What's the optimal sequence? Well, step 1, you floor it. You accelerate toward your destination at your absolute maximum capability until you hit the exact midpoint of your journey. Then, step 2, you instantly flip your thrusters and decelerate, braking by that exact same amount until you gracefully arrive at your destination at exactly 0 speed. And just for the sake of our thought experiment, let's assume we can actually change our acceleration instantly in literally 0 seconds.
So, how long would a trip like this actually take? To figure this out, without, drowning in complex calculus, we can use this incredibly powerful trick called dimensional analysis. We know the final answer for time has to depend on distance and acceleration. To get our unit of seconds, we normally divide distance by acceleration and then take the square root. But we're in our logarithmic magnitude scale, so division just means subtraction, and taking a square root, that literally just means dividing the magnitude by 2. As our rule shows, we take the distance magnitude minus the acceleration magnitude and divide the whole thing by 2. It's wonderfully elegant.
There is a tiny catch, though. Dimensional analysis has a bit of a blind spot. It doesn't always capture the exact prefactor. See, because of the geometry of how speeding up and slowing down actually works, our magnitude is slightly offset by a prefactor of 2. And on the logarithmic Immusora scale, a factor of 2 translates to a magnitude of 0.3. So to get our perfectly correct final time magnitude, we just have to remember to add this 0.3 offset back into our final calculation.
Now, I can already hear the metrologists out there saying, wait, so it's not perfectly exact right out of the box? But this actually highlights a really key philosophy in physics. Order of magnitude estimation isn't always about absolute perfection down to the final decimal point. It's really about just getting us in the right ballpark. It tells us whether a trip is going to take a few minutes, a few hours, or a few years.
Let's actually test drive this math on a real journey. Let's go to the Moon. The Moon sits at a distance magnitude of 8.5 meters away. And let's assume a maximum acceleration magnitude of 0.7. If we use our rule, 8.5 minus 0.7 equals 7.8. Divide that by 2, and we get an estimated time magnitude of 3.9 seconds. Now, if you translate that back into conventional time, it's about 2 hours. The perfectly exact answer is 4 hours, but look at how crazy close we got. We instantly know it takes a few hours, not an entire year. The math works beautifully.
Okay, let's push the limits a bit. The Moon is practically our backyard, right? Let's aim for something truly epic. Next stop, the nearest star to our solar system. We've got our trusty formula. We've got our maximum acceleration. Let's find out exactly how long interstellar travel actually takes.
All right, let's run the numbers. The nearest star is at a massive distance magnitude of 16.6 meters. Let's say our shiny new futuristic ship can pull a continuous maximum acceleration of 1.0 meters per second squared. We do the math. 16.6 minus 1.0 is 15.6. Divide that by 2, and our estimated travel time is a magnitude of 7.8 seconds. And if you translate that magnitude into conventional time, it equals about 2 years. Wow, 2 years to reach the nearest star.
But wait, hold on a second. If you know anything about astronomy, literal alarm bells should be ringing in your head right about now. 2 years to another star system? That definitely doesn't sound right, does it? The math was absolutely flawless. The dimensional analysis was solid. So, where on earth did we go wrong?
Well, here is the massive hint that blows our entire calculation wide open. A light year is a distance magnitude of 16.0 meters. Light is literally the absolute fastest thing in the universe, and it takes light a magnitude of 0.6, which is 4 conventional years, just to travel to that exact same nearest star. Our math said we could do it in 2 years. Guys, we accidentally just built a math equation that allowed us to travel faster than light.
And honestly, this perfectly captures the massive historic shift in our understanding of physics. See, when we were doing that math, we were relying on pure Newtonian principles. Sir Isaac Newton's laws assumed that if you just keep accelerating, your speed can just increase infinitely forever. But it took humanity until the early 20th century for Albert Einstein to come along and figure out the real story. Einstein revealed that light does not have infinite speed. In fact, nothing, literally nothing in the entire universe can move faster than light in a vacuum. We essentially hit an invisible cosmic wall.
So, what does this all mean? Does this mean our dimensional analysis and all those cool immeasurance calculations we just did are garbage? No, not at all. The math is still a highly accurate, incredibly reliable tool. As long as we stick to speeds that are much lower than the speed of light, like flying planes, launching satellites, or even just hopping over to the moon, we can make highly accurate measurements using those classic Newtonian principles. The math is totally right, we just have to respect the physical laws of the universe.
Which brings us right to this final, ultimate reality check, 16.0 meters per second in magnitude. This isn't just some random number. It is the cosmic speed limit. It is the absolute maximum speed anything can possibly travel in empty space. No matter how incredibly powerful your engines are or how clever your math is, the universe rigidly enforces this boundary. But it does make you wonder, if we can never ever break this speed limit, what other creative ways is humanity going to have to invent to truly explore the stars? Something to think about. Keep wondering, and as always, keep looking up.